Hello students, welcome back to the session. Today we are going to continue the discussion on the electromagnetic induction. In this chapter I am going to discuss the topic energy stored in an inductor. So how much will be the energy stored in an inductor? How the energy gets stored, in what form the energy is stored, these are the things which we have to discuss. Now energy stored, how? We know that inductor works on the principle of electromagnetic induction, which means that an EMF gets induced when the magnetic flux linked with the coil is changing. So what we can say is, in the induced field, energy is getting stored up. So what is the form in which the energy is stored? Students, please remember, in an inductor, the energy is in magnetic form. If you try to recollect, in a capacitor, the energy was in electrical form. If you remember, you say energy stored in a capacitor is half CV square. That energy is in electrical form. In an inductor, the energy is stored in the magnetic form. So we say the energy is stored up magnetically. Now, the question arises, how exactly to measure that energy? So in order to measure the energy, we can use the concept of power. Now we know power is equal to VI, correct? This is known to us. So therefore here we can write power is equal to E into I. E is equal to L di by dt. I am taking the magnitude into I. This is what we have. We know induced EMF E is minus of L di by dt. Here I am taking the magnitude of the power. So I will write it as L di by dt. This power. And power is what? Rate at which energy is consumed. We can write like this. Therefore, dW will come out as LIDI. This is what we get. So integrating both sides, what we get? Integration of dW is equal to L integration of IDI. What will be the limits of integration? The limits will be from 0 to I. So now when we integrate dW, so what we get? We get something like this. W is equal to L and I square by 2 from 0 to I. So there, this energy is stored, this work done is stored in the induced field in the magnetic form, and we say U is equal to half Li square. This is the total energy. This is the total energy stored. Now, if you remember, in case of capacitor, the same equation, similar equation, we had half CV square. See, here we are getting half Li square. This is the total energy. Now, the next thing that we need to find is what is called as energy density. The next term is energy density. Energy density is represented by small u and B here. Please understand the symbols. This is U is the total energy, B is represents the magnetic field. Sometimes in the numericals these symbols are directly used, so it should be known to you. So what exactly is energy density? Energy density is total energy stored upon volume. This gives us energy density, energy stored per unit volume. So if you want to define energy density, you can define it this way. It is the total energy stored per unit volume of that field. Like say for example electric field. So you get U small, we write small u subscript E. This is energy density for electric field. Same way if you have energy density for magnetic field, now total energy is known to us, that is half L I square. This is volume. Now volume will be what? Area A into length. This will give us volume. Now this equation, if I try to write, this is the equation for the energy density. Now suppose if we use a solenoid, then the value of L for a solenoid is known to us. We have derived it in the previous class, right? For a solenoid, L is equal to mu naught N square A by L. This is what we have seen for a solenoid. So therefore U of B will become half, this is mu naught N square A by L. This is half L I square upon volume is A into L. Now simplify this. If we simplify this, what we get? Half. Mu naught will remain like that. N square will remain like that. A cancels, upon L square we will get. And I square we will get. Now see, a small change in the equation if I do, I can write like this, half 1 by 2 mu naught, and here I will write it as mu naught square, and this is N square by L square I square. This is what we get. This can be written as 1 by 2 mu naught. I can write this as N by L whole square, and this is mu naught square N by L whole square and I square, correct? Simplify further, 1 by 2 mu naught, this is mu naught N by L into I whole square. Now what is this? This equation can also be written as 1 by 2 mu naught N I square. This expression is B for a solenoid. We have considered solenoid, na? So this is B for a solenoid. So this can be written as 1 by 2 mu naught into B square. This is the expression for energy density of magnetic field. Compare it with the energy density of electric field. If you have electric field, you had 1 by 2 epsilon naught E square. Now observe here closely. You will say that in this equation probably is for a solenoid. No. This is a most general equation. How can we say that? See here. Is there any term in this equation which represents specifically for a solenoid? Is there any term? See, every term which is making this equation specific for a particular kind of coil is eliminated. How? See here. 1 by 2 is a constant, mu naught is a constant. B is the strength of the magnetic field. Now it can be a solenoid, it can be a circular coil, it can be an infinite straight conductor. So accordingly find out the value of B and substitute. So how this equation is dependent on the nature. See, we started with solenoid. Why? Because we wanted to get rid of L. L is what? L depends on type of the current carrying conductor. So in order to make it free from L, in order to make it free from area, otherwise area gets defined for a square, for a circular cross section. So this equation is independent of all such parameters. That is why we say this equation is a general expression for energy stored in the magnetic field per unit volume. Now suppose you want to calculate what is the total energy. No problem. You know energy per unit volume. Multiply by the volume in which you want to find the energy stored. You will get total energy. That is exactly how the importance of total energy stored can be understood. Now students, let us discuss about eddy currents. This is a completely theoretical topic. This topic may be asked in a short note. This is for your information. This thing is a complete theoretical. Eddy currents are the currents which are produced in the core of a coil. Core of the coil means what? See, if you remember, in case of transformer, in case of a transformer, we had a core like this, and then we had primary turns here. We had primary, we said primary, then we said this as secondary. This is what we had seen. Now see, because this is metallic, so what happens is, in the core of this transformer, this is called core. Now the flux linked with the core is changing. So an EMF is induced in the core, in the body of that transformer. Since it is metallic in nature, it will have some resistance, so that induced EMF is getting converted to induced current, that is eddy current. So eddy current is the induced current which is produced in the metallic frame or the core of the coil, which is having change in the flux linkage. Because of the change in flux linkage, EMF will be induced. That is known to us from the Faraday's laws of electromagnetic induction. Now in this frame, if you remember, that is why we told that to minimize that loss we are taking laminated core. See, because to minimize iron losses, they are also known as eddy losses. So this sometimes this eddy current is used as an advantage, sometimes it's a disadvantage as well. Like say in case of induction furnace, we are using the energy carried by the eddy currents. They are capable of producing heating effect. So we are using that. So induction furnace works on the principle of eddy currents. There are certain measuring instruments which are also working on the principle of eddy currents, because eddy currents will oppose the motion. So the needle will come to rest immediately because of the eddy current which will oppose the applied current. So that is exactly how eddy currents are used in advantage. Somewhere it is disadvantage, like see in transformer it's a disadvantage. It is causing loss in the power. So sometimes eddy currents are also known as focal currents. So be very careful. It is not necessary that the examiner will give you in this name only. It might be mentioned as a focal current also, because it was first of all studied by Foucault. That is why it is named after him as Foucault's current. That is about the eddy currents. It's a totally theoretical topic. No numericals can be there from eddy currents. Now students, let us take the application of EMI. One application we have already seen, that is transformer. There is one more application that is there, that is AC generator. See, the AC generator can be called as a block diagram for AC generator. in an AC generator. First of all, we need to understand how come this is a part of application of EMI. If you remember in the last class when we discussed the factors affecting EMI, one factor was orientation. This particular device works on that particular factor. How? Let us understand it. We know phi is equal to B dot A. This is known to us. See, this is the fundamental equation of EMI. This can be said as BA cos theta. This can also be said as BA cos of omega t, because angular velocity omega is theta by t. We know this, na? So we can say angular displacement theta is omega into t. This is what we have as phi. See the transformation. Because there is rotation in this coil will rotate. Now, what we saw, the third factor which is capable of producing induced EMF is change in the orientation. Means theta is changing with respect to time. This means differentiate this equation with respect to time. So d phi by dt, B is constant, A is constant, theta is changing, so we will write cos omega t. See, this is what we can have. So what d phi by dt, so B, A. What is d by dt of cos? Minus sine, and omega t will come as it is, into apply your rules of differentiation, where we have omega t is to be differentiated, that is omega. So finally what we get? Minus of d phi by dt is equal to BA omega sine of omega t. Now what is minus of d phi by dt? This is induced EMF. So induced EMF is equal to BA omega, and I can write omega t back as theta. This is exactly what we get. So this is the induced EMF which we are getting. See how the orientation is generating induced EMF. This induced EMF is the current which you are getting here as output. Here we are drawing the current output, induced EMF. Now, how exactly, what is the nature of this induced EMF? Nature, what it means is, it is a function of theta. Observe this. It is a function of theta. So I can write E is equal to this BA omega, I can write as the maximum value, and we can write it as sin theta. Why are we writing this as maximum? Because what is the maximum value of sin theta? Plus 1. The maximum value of sin theta is plus 1. Therefore, what will be the maximum value of EMF? BA omega. So I can write that as maximum value. Here, if theta is 0 degree, E is 0. Theta is 90 degree, E is E max. Theta is 180 degree, E is 0. Theta is 270 degree, E is minus of E max. Finally, theta is 360 degrees, E is again 0. See, I have taken one complete rotation of the coil. See, this coil is this way. One complete rotation, see, this is 180 degree. Again you take it full, then it becomes 360 degree. So complete 360 degree I have taken. And what we observe, if you try to plot the variation, how? See, let us say this is E naught or E max, and let us say this is minus of E max. This is 0 degree. This is, let us say, 90 degree, so I will write pi by 2. This is 180 degree. This is 270 is 3 pi by 2. and this is 2 pi. Now plot the graph. If you plot the graph, what do you see? If you plot the graph here we have Emax, this is minus of Emax, 0. When E is 0, it is 0. It is 90, it is plus. So here 180 is 0. This is here and this is here. Join with a smooth freehand curve. So what we find, for one part it is plus, for one part it is minus. How to distinguish where it is plus and where it is minus? See, if you carefully observe, this is one time period, means it took, what is the meaning of time period? Time period is the time taken by the coil to complete one rotation, that is 360 degree. So this becomes T by 2. So what we observe? There is change in the direction of the EMF every half cycle. If you extend this, see, if you extend this, again you will get something like this, na? This means you are getting plus. See, it is alternating, na? That is why it is called alternating current. So what alternates in this? Polarity of the current is reversing every half cycle. That is why it is called AC generator. It is not AC. If it is DC, then in DC there is no change in the direction, there is no change in the polarity, it remains fixed. That is why in DC appliances, if you have observed, plus terminal and minus terminal are marked. That is DC appliance. You can take the reverse also. Those devices in which plus and minus are marked are DC. Like say the torch, dry cell, you see, in that plus and minus is marked. Now you reverse one of the dry cell, the torch will not glow. It is DC. But if you have observed the 3-point plug, there is no plus and minus marked there, because the source which you are using is AC. If you put a plus sign, then the next instant it would become minus, because it is alternating. And if you have observed your main supply, you write 50 hertz. See, that is the frequency. You take the reciprocal of it, you get the time period. In that much time, there is a reversal in the polarity. That is why in 3-point plug you will not find plus and minus being marked, because it is a AC. While in DC, see, in torch, in those dry cells, plus and minus is marked, because it is a DC source. That is how we can identify. And you see, numerically we have established also, if the polarity it varies, like say dry cell is 1.5 volt, na, straight line you will get. You will not get a negative, na. 1.5 volt you will mark it, you will get a straight line. With passage of time, there is no change, it will remain 1.5 volt, na. This is what is the variation of E with time for a DC. It is a straight line. Frequency will be 0 for a DC source. All these information we will take in depth when we will take up the chapter alternating currents. Now, to make you understand how exactly it is named AC, that is why I have taken. Please see, these polarities are reversing. That is why it is called AC generator. See, here we are generating by the movement of the coil. By the rotation of the coil with an angular velocity omega, we are achieving this. That is exactly how. Now closely observe. These are carbon brushes. The C which is mentioned is carbon brush, through which we are drawing the output. Here we are drawing the output current through these two terminals. Okay. S is split ring. They are known as split rings because it is alternating. right? So that is why we have a split ring. If I want to convert this into a DC, instead of split rings, I will put split ring commutator. Then we can convert. And that is exactly how you are supposed to understand this concept, the concept behind AC generator. It is generating, it is converting the mechanical energy into the rotation that you have given. You have given rotation to the coil. So the rotation mechanical energy is converted to electrical energy. That is how AC generator works. So how can we say what is the working principle? Working principle is based on the fact that whenever there is a change in the rotation orientation of a coil with respect to the magnetic field, an EMF is induced. This is exactly what is the working principle of AC generator. Well, students, let us discuss one topic which is very important from the entrance exam point of view. This topic is said to be growth of current in an LR DC circuit. L is what? Inductor. R is what? Resistor. This is what? Growth of current in a. So if we try to understand this in the form of a circuit diagram, it will look like this. This is one resistor, this is one inductor, and we have a DC source. Key is placed. This is exactly what we have. This is R and this is L. This is what we have as LR DC circuit. If here the source is placed AC, then becomes a AC circuit. Right now let us discuss about the DC. Now students, observe. Why do we say growth of current? Because we have seen in the previous classes, induced EMF in an inductor is given by minus L di by dt, which means I is a function of time. I is changing with time. Strength of current I is changing with time, which means current is growing. If the key is switched on, then the current is increasing. That is called growth. If I switch off, then the current starts decreasing. That is called decay or decrease of current. Now, since we say growth of current, current is growing. So current will follow some function of time. With time it is growing. Now with time it is, the value of current is changing. So it is growing with time. Then the question arises, this function is what? Is it a logarithmic function? Is it a exponential function? Is it a trigonometric function? Is it a algebraic function? What kind of function is it? This is what we have to find. The kind of function it is. What is the dependence equation of current with time? So in order to find that, I am using Kirchhoff voltage rule or KVL, voltage law, or you can call it as loop rule, any one. Apply loop rule and what we get? E minus L di by dt is equal to I into R. This from what we are getting? This we are getting from loop rule. Loop rule is Kirchhoff voltage law. KVL also it is known. E minus L di by dt is IR. This is what we can write. So therefore I can write it this way. E minus of IR is L di by dt. This is what we can write. Now di, see here, di upon E minus I into R is equal to 1 by L into dt. This is what we are getting. Now see, I is on one side, other terms are on one side. Now let us integrate this. So integrating both sides, what we get? Integration of di by e minus ir is equal to 1 by L is a constant, integration of dt. This is what we can write. So what will be the integration of di upon e minus ir? You have done integration. Do this integration by substitution method and you must get this as minus of 1 by r log of e minus ir. This is to the base e, because in calculus all the log terms are to the base e unless until specified. This is written as 1 by L into t plus constant. If you remember, integration can be definite, can be indefinite. Here we have not taken any limits, so there will be a constant of integration. Now our aim is to find what is the value of this constant of integration. To find the value of the constant of integration, we must know the boundary conditions. Boundary condition means some values of I at a given value of t. Okay, we know when t is 0. What is the meaning of t is 0? T is 0 is a condition when just you closed the key. Just when you switch on, the current started from 0. So I is equal to 0. This is what we can say. Substitute these boundary conditions in the given equation. If we substitute the boundary conditions in the given equation, what we are getting? What we get is minus of 1 by r log of e, and e, because I is 0, is equal to 0 minus of 1 by r log of e, I is 0 is equal to 0 plus constant. So the value of the constant is minus 1 by r log e. Substitute the value of the constant here. So therefore we will get minus 1 by r log of e minus ir is equal to what we get? 1 by L into t plus or minus 1 by r log e. This is what we are getting. There are two log terms, right? We can simplify it, or I can write log of e minus ir is minus of r by L into t plus log e. We can write like this as well. So there are two log terms, so that can be condensed into one, and we can write it as log of e minus ir upon e is equal to minus of r by L into t. I am continuing that here. So what we got? Log of e minus ir upon e to the base e we got as minus of r by L into t. Convert the log expression into exponential form. This can be written as e minus ir upon e is equal to e power minus of r by L into t. That is exactly how we can convert logarithmic form into exponential form. Now rearrange the terms. If we rearrange the term, we get e minus ir is equal to e into e raised to minus of r by L into t. So bring this side, so we can say e is common, 1 minus e raised to minus of r by L into t is equal to ir, or I can write I is equal to e by r 1 minus e raised to minus of r by l into t. Now what is E by R? See here, this is E, the voltage here, this we say it is E by R. This is the maximum value of current that can be there in the given circuit. So E by R is the maximum value. So we can write I is equal to I max and 1 minus e raised to minus of r by L into t. This is the equation. So come to this. So what exactly was our starting thing? We started with the discussion that growth of current means current will grow with respect to time. Then the question arises, what is that function with time? I will be some function of time. Some function means it can be logarithmic, it can be exponential, trigonometric, algebra, many different type of functions. See, we have concluded it is nothing other than exponential function. So current grows in an LR circuit in exponential terms. Please remember, this is the normal type of questions which are framed in objective questions theoretically. So the current relation, this is only for growth of current. Now many situations we can extract. First thing that comes to our mind is how much time will the current take to reach maximum value. Since we say that I is a function of time, so what is the next step? The next step is how much time will the current take to reach the maximum value. So all those things we have to find out. Now see, let us take that discussion. Time taken by the current to grow to the maximum value. What exactly we mean by that? What we mean is, see this, when I is equal to I naught, when I is equal to I naught, what will be the value of time? This is the question. We want I is I naught. Now what we know, this is growth, na? So we know I is equal to I naught into 1 minus e raised to minus of r by L into t. What is given? I is equal to I naught. Put the value of I is equal to I naught. What you will get? And simplify mathematically. So 1 minus e raised to minus of r by L into t. So what we find? I naught gets cancelled out. If I naught get cancelled out, what is the equation you are getting? 1 is equal to 1 minus e raised to minus of r by L into t. Simplify this further. So what you will get? 0 is equal to e raised to minus of r by L into t. So what will be the value of t here? So in order to get the value of t, please see the equation. Don't jump into conclusion just like that. Negative power means what? Reciprocal. So that is very important. So 0 is equal to 1 by e raised to r by L into t. So we can also say e raised to r by L into t is equal to 1 by 0. So from this what we conclude? We conclude t is infinity. See. So how much time will the circuit take to reach maximum value? Infinite time. So it is taking infinite time for the current to grow. Can we wait for the infinite time so that the current will grow to the maximum? Definitely not. Then what is the solution? When can we say that the current has stabilized in the circuit? For that we need to see the variation of current with time. If we plot a graph, see, if we try to plot a graph of I versus t, what is the kind of graph that we will get? See, this is t here and this is I here. I am plotting I this side. So what is the graph? Okay, to plot the graph, what did we see? When t is 0, I is 0. So your graph will start from this point. When t is 0, I is 0. Then what do we say? What do we see? That when I will be I max when t is infinity, and the growth of current takes place exponentially. This is the nature of graph. It is exponential graph. Observe the graph. Up to certain time, the graph is steeply increasing. What is the meaning of steep increase? It means that slope of the graph, observe the slope of the graph is large, which means y coordinate change is very large in comparison to a x coordinate change. So which means that in a small time large current is generated. This is steep increase. After that you observe the graph is becoming flat, which means that the slope is decreasing. If the slope is decreasing means what? Change in the y coordinate is small for a given change in x coordinate. So current is not increasing after that time. So let us say if we try to locate that point, observe, it can be said as this is the point. Up to this point, observe the slope of the graph is very large. After that you draw tangents, you will find that the slope is less. How to locate this point? How to locate this point? See, if you draw tangent here, this is becoming asymptote, na? So this is I max. Then how much will be this? Okay, so our now aim is to find what is that value of t. This I have represented by a symbol. This is called time constant. How to find that? Absolutely no problem. See here, in this equation of current, what we have? In the equation of current, I is equal to, we have I is equal to I max 1 minus e raised to minus of r by L into t. In this, when t is equal to, that is L by r, put the value of t as L by r, then what will be I? That is the I. So we have to find that value of I. So how will you find that? Put the value of t as L by r in this equation. What you will get? I is equal to I max into 1 minus e raised to minus 1. Put t as L by r. Cancels, minus 1 we get. How much will be e power minus 1? E power minus 1 is 0.368. This gives us I max into 0.632. This is the value of current there. This is nothing but 63.2% of maximum current. So what is the interpretation? What is the meaning of this? This means, see here the I here is 0.632 of I max. So it means that when the current in an LR DC circuit has reached 63.2% of its peak value, we can assume that the current is stabilized. We can assume that the current is stabilized. So that time is known as this time, which is equal to L by R, is called time constant. This is called time constant. So what is time constant of a LR circuit? Time constant is that time in which the current becomes 63.2% of its peak value. Suppose that the maximum, suppose E is 10 volt, R is 10 ohm. How much will be the maximum current? 1 ampere. 1 ampere is the maximum current. Time constant will be how much? 0.6. R by L is your, L by R is your time constant. We know the value of L, we know the value of R. That will be the time constant for the growth. It is not for any situation. It is only for the growth of current. So this graph tells us, if we plot that L by R as the time constant on the time axis, we will get 0.632 of Imax. This will be used in numericals extensively. So students, this, if you are wondering how did we get this value of e power minus 1 as 0.368, value of E is 2.718. You take the reciprocal of it, you will get this value. That is exactly how growth of current in two situations. What is the function of current with respect to time? Exponential function. This is the first information we get from this. Second information, the equation is given as I is equal to I naught or I max. Somewhere, some books you will find it is written as I naught. This will be written as I naught, same as I max. 1 minus e raised to minus of R by L into T. This is the expression for growth of current. Next important point. What is the time taken for the current to grow to the maximum value? Infinite. The circuit takes infinite time for the current to grow to the maximum value. Next, how can we say that the current is stabilized in an LR circuit? When the strength of current in that LR circuit is 63.2% of the maximum value of current, then we can say that the current is fairly stabilized in that circuit. These are the key points which you have to keep in mind. The moment you read the word growth of current in the numericals, these points should always flash into your mind. Well students, now let us discuss the second part of the LR DC circuit, where we say decay of current. Decay here doesn't mean that current is decomposing, it's not that. Decrease. Decay means decrease. So decrease of current. So the question arises, in an LR DC circuit, this is an LR DC circuit. This is key, this is EMF E, source you have placed, this is R, this is L. Decrease of current. So the question arises, as we had argued in case of growth of current, the decrease, does it happen linearly or not? If not, why? If yes, how? So many questions arise in our mind when we read the word decay of current. We cannot assume anything from our side, because circuit will tell what exactly is the function which is responsible for the decrease of current, which means that again here this decrease of current will be some function of time. What is that function? Is it logarithmic function? It is algebraic function? Linear? What type of function? This we have to find. In order to find the expression or the function of time, we need to know how exactly I changes with time. So how to get that? So to get that, see here, when will decrease happen? The decrease happens when the key is open. Simple thing. In a household circuit, when you switch on, current flows, you see the effect, light glows, fan starts moving and all. This is exactly what we say as growth of current. Now the moment you switch off, that is the time when the current starts decreasing. It will be switched off. The key will be compulsorily in the off position. In the numericals, this is the data which you have to carefully identify from the statements. So for decay of current, it can no longer be connected with the source. In the question numericals, it will be given to you. An inductor of 10 millihenry and resistance 10 ohm is connected with the source. See, it is given, it is connected with the source. Compulsorily growth of current will happen in that circuit. If it is given that when disconnected from the source, then in that situation decay of current is going on. Accordingly, we have to use that function of time for the expression of current. So here, by using, how will we find the expression? You have done Kirchhoff laws, right? So here, use the voltage law, or if you name it as loop rule, anything, but use the rule which involves voltage. Fine. So if we use voltage rule, what we can say, from loop rule I am saying, from loop rule, E, this is opposite, so minus L di by dt, so this is in the same direction, so it is IR. This is what we get as the expression for this particular situation from loop rule. But K is open, this means E is 0. If K is open, E is 0. Therefore, what we get? Minus of L di by dt is I into R. As simple as that. Now we can rearrange the terms containing I towards the side which contains a di, and we can integrate. So what we can say now? Di upon I. See, this I am bringing to the denominator, so we get this as minus of R by L into dt. See how easy it is now. Now integrate both sides. Now integrating both sides, what we get? Integration of di by I is equal to minus of R by L integration of dt. So what we get? What is integration of 1 by I? Integration is log of I to the base E. This is what we get, is equal to minus of R by L into T plus constant C. This is what we get. Now we have to find out the constant of integration. How to find this constant C of integration? We know when T is 0, how much is the value of I? What is the meaning of the statement? Please understand before you answer this question. What is the meaning of T equal to 0? T equal to 0 is that instant when you switched off. T is 0 is that instant when you switch off. At that time, whatever is the strength of current is your I. Assuming that the current would have reached its maximum value, so the current will decrease from the maximum value. So at T is 0, we will assume theoretically that the current is decreasing from maximum value, it will come to 0. So therefore I is to be taken as I naught. Please remember this. The exactly reverse was there in growth of current. In growth of current, when T is 0, this means when you switch on, before that the light tube lights were not on. When you switch on, then they start glowing. This means when T is 0, at that instant current was also 0. From 0 it will grow to the maximum. That is growth of current. But in decay, it has reached its maximum. From maximum it will come down. So we say theoretically at T is 0, in decay of current I will decrease from maximum. Please understand this because this is very much essential. Otherwise you will not be able to find out the value of C. Substitute this C here. So what we get? Log of I to the base E is equal to minus of R by L into T plus log of I naught, which is the maximum value. This is exactly what we get as the expression. Now there are two logs. Let us try to evaluate. So what we get now? Log of I to the base e minus of log of I naught to the base e is equal to minus of r by l into t. So we get log of, you know this, 2 log, there is a minus sign. So I by I naught is equal to minus of r by l into t. So what we get now? I by I naught is e raised to minus of r by l into t. So the expression we get as I is I naught e raised to minus of r by l into t. See, this is the decay equation. I is equal to I naught. What was the growth equation? I is equal to I naught into 1 minus e raised to minus of r by l into t. While for the decay equation is this. Now again we have to find out what is the time it will take to become 0. Decrease, na? How much time will the current take to become 0? So can you try this? Please try that. In the meantime, yes. Now, first situation, when I is equal to 0, t will be how much? This is first situation. Put I is 0. So what is the decay equation? We know I is equal to I naught e raised to minus of r by l into t. I is 0. So 0, what we get? 0 is equal to I naught e raised to minus of r by l into t. So what we get? E raised to minus of r by l into t is equal to 0. Remember the previous equation. Same thing. 1 by e raised to r by l into t is 0. This means e raised to r by l into t is 1 by 0, and 1 by 0 is how much? Not defined, infinity. So from this we can say t is. So what is the conclusion? The RL circuit will take infinite time for the current to decrease to 0. So can we wait till that time? Definitely not. So when can we say that it is very safe, the current is no longer there in the circuit? Practically. Theoretically though it takes infinite time. So practically what it is? Again we have to use the same condition that we had seen in growth of current. So now here what we will say is, what is the strength of current when? So in order to find that, again plot I versus t graph. If you plot this, what you will get? We will get a variation, something like this. This is t and this is I. Now what did we see? When t is 0, how much is current? Maximum. So your graph will start from where? From maximum. This is your I naught. From maximum it will start, and then it will go to infinity. It's an exponential graph. So a steep fall, and then it will become asymptote to time axis. See, this is exactly how the graph goes. Now observe, up to certain time it is very steep, after that flat. So let us say this is the time, right? This time we will say it is time constant. So this time constant is, we are taking L by R. So now we will find that value of I. So when, second case, see, when t is time constant, which is L by R, then I will be how much? Substitute. I is equal to I naught e raised to minus of r by l into t, and the time constant L by R. So this means I is equal to I naught e raised to minus 1 How much is e raised to minus 1? 0.368 I naught. So that is 36.8% of I naught. See here. This is exactly what we say. So this I is how much? This I will be 0.368 I naught. So what is time constant? That is why in the beginning I told it is not constant for all situation. Time constant for decay of current in an LR circuit. What will be the time constant? It is the time taken for the current to decrease to 36.8% of its peak value. So practically, if the maximum value of current is 1 ampere, now if it decreases in the circuit to 0.368 ampere, we can say fairly the current has become negligible. Current has become negligible. Practically it is not zero. There is current. So the question arises, it is not zero. What is happening to the remaining? Where is that energy associated with the current going? So many questions arise in our mind and they form the basis of theoretical question, reasoning question in the entrance exams. That is why you need to think what happens to the current which is less than this. Let us say for example 30% of I naught. 36%, when it has come down to 36% below, it is not going to zero. Let us say 30%. Where is that energy going? So what we say is, since the wire through which you are passing current has some resistance, so the resistance property of the connecting wires are now dominant. The strength of current is becoming weak if it is less than this. It is not able to give sufficient energy to the electrons so that they can move. The resistance property of the conductor becomes dominant. So the electrons with energy less than this are getting blocked by that conductor. That is the reason why we don't see any effect. To see effect, strength of current should be greater than 36.8% of peak value. If it is less, you will not see any effect. That is exactly what is the reason. And because of this reason only, inductors, even if it is, see the choke coil, if you remember I had given you where practically we see the effect of inductance, choke coil. It is having energy in it. We are not supposed to touch the connecting wires with just like that, because there is energy, it might give you an electrical shock. So we are not supposed to hold it by the connecting wires. Now you will say, how to identify whether there is current or energy or not? Very right. The choke coils, those wires, if you touch, you will see sparks coming out. From where the spark came? That spark is nothing but energy because of the current less than this converted into heat and light. That is what is spark, and that is exactly what we see. So safety device, safety thing, never touch used inductor choke coil by their connecting wires. You should always hold it from the body of that device. That is how growth and decay of current is to be understood.